we will look at how to eliminate the possibility of having a glitch in the output of a more finite state machine by eliminating the output logic. You're not seeing double. This is going to be my original finite state machine that I will leave unmodified, and over here we are going to modify it so that we eliminate the output logic, which means that there won't be any glitches. The output's just going to be a direct function of the state. No need to have any logic gates there. So what does this code do? Well, I just made it up, so it doesn't do very much, but I've got 4 states. I've got my flip-flops here. I've got my next state logic. I just have 1 bit as input, so whatever the current state is and the input is, this tells me what my next state is, and my output is a 1 if and only if I'm in state D. I need to have output logic here to compute this. In particular, it's going to be an AND gate. The state, the 2 bits of the state will go into an AND gate to work out whether, under this state representation, to work out whether or not I'm in state D, because D's given by a binary 1, 1. Given the Verilog code, it's actually very easy to eliminate the output logic. Basically, we just have to pre-compute the output by not using state here, using next state, and then that will give us what we will call next out, and we just put that through a flip-flop to delay it. Because we've pre-computed it, it's too early to actually output it. We need to wait for the next rising edge of the clock, and then we can use flip-flops to do that. So let's go ahead and do this. Initially, it won't quite be in canonical form. It will be correct, but it will not be in canonical form. Then we modify it to bring it into canonical form. The first thing we do is we pre-compute the output. So we're going to give it a different name, next out. This is not the current output, but the output we want at the next rising edge. And all we do is we say that that's the same expression as before, but we use next state instead of state. So we pre-compute the next output. And by the way, this is the benefit of having our finite state machine in canonical form. It's very easy to make such modifications. So we've pre-computed our output here. We need to store it somewhere. I'll add a wire here, next out up here. What's our actual output? Well, our output's not equal to next out, because then our output would change too early. We need to delay it. We need to wait for the next rising edge of the clock, and to do that, we need a flip-flop. So at the next rising edge of the clock, we're going to say that out takes the value of next out. So we pre-compute it, we wait for the next rising edge, and then we output it. So that means that my output up here needs to be made a register. It used to be a wire, it's now a register. Because it's now a register, because it's now a flip-flop, we need to initialize it, because we need to have an output right at the start. So initial out equals, now how do we initialize it? Well, our finite state machine, it starts off in state A. That's how we initialized state. And if we're in state A, then the output is going to be a 0, because the output is only a 1 if we're in state D. So the correct way to initialize out is as 0, because that's the correct output when we're in state A, which is how we initialized state. So in one sense, we're now done. This new finite state machine is exactly the same as the old finite state machine in terms of its input-output behavior. If someone were just observing the input-output behavior, they cannot tell the difference between these two, if I haven't made a mistake. But this second finite state machine is guaranteed not to have any glitches on the output, because there is no output logic. The output is directly taken from the output of a flip-flop, so there's nothing there to cause glitches. However, this isn't quite in canonical form, and it's good for us to understand what we've actually done by rewriting this in canonical form. So the first thing we have is we can't have more flip-flops down here. All our flip-flops live up where the state lives. And indeed, all we've actually done is we've added a new state. We've augmented our state so that the pre-computed output is now part of our state. And so the current state is going to take the value of the next state at the next rising edge of the clock. So I've just moved our flip-flops up there so I can delete this. We have initialized our output. So up here we see that basically out and state, the pair together, they are our state. And then we've got next state and next out, they're our next state. Here we've got our flip-flops. Then down here, this is our next state logic. And assign next out equals next state, etc. That's part of the next state logic. We could actually combine it in to the single always block, but it's always better to have lots of short blocks rather than one long block because it's easier to debug. So this is simply part of the next state logic. You might argue, but hold on, how can this be part of the next state logic if it's a function of the next state? Well, next state is a function of the state, and so next out is also a function of the state. So this is just an algorithmic way of computing the next state. What about our output logic? Well, exactly, we do not have any output logic because the output is simply part of the state. And so we really have eliminated the output logic. There is no output logic in this second finite state machine, whereas over here, this is our output logic. This is our next state logic, output logic. Here, we've got next state logic, no output logic. At this point, we're basically done. It's important to emphasize that the state diagrams for these two finite state machines are identical. All we've actually done is change the state encoding. We haven't actually changed any of the state dynamics. So if you were to take this finite state machine and draw the state diagram, you would have 4 states and they would transition according to the rules here. If you were to draw this state diagram, you'd still only have 4 states. Yes, you're using more bits to store the state because the state's now both out and start, so it's going to be 3 bits. But not all combinations are possible. Indeed, the next out, and therefore out, is fully determined by state. Next out's fully determined by next state, so we haven't actually added any more states. We've just changed the state representation. It might be that we can change the state representation yet again. If we want to eliminate output glitches, we must have that out is part of the state, but maybe we can simplify our state representation, our ABCD. Maybe we can reduce it. In this case, I don't think we can, but in some other cases, that may be possible. Such a reduction has got nothing to do with the state diagram. The state diagrams are identical. It's simply choosing a state representation such that the output is simply a subset of the bits making up the full state. That's how you eliminate any potential for glitches on the output.